All right, welcome to lesson 1.9. We're going to be talking about describing location in a distribution. So the essential question we want to address today is, how do we determine where an individual is relative to other points in a given distribution? So we want to be able to find and interpret various measures of location, including a percentile in the distribution of quantitative data, estimating percentiles in individual values using a cumulative relative frequency graph, and finding and interpreting a z-score in the distribution of quantitative data. In order to understand this, we need to understand what a percentile is, what a cumulative relative frequency graph looks like, and a standardized score or z-score. All right, so here are the scores of all 25 students in a statistics class on their very first test. So the scores are given below. Now the bold score is Jenny's score, and she got an 86 on the exam. How did she perform on this test relative to her classmates? So the dot plot below actually displays the scores for you. Jenny's is marked in red. The distribution is roughly symmetric with no apparent outliers. From the dot plot, we can see that Jenny's score is above the mean of the distribution. It's above the middle of the distribution. And we can also see that she did better than most students in the class. So what we want to do is, essentially, how do we determine the measure of location? How do we determine how she did relative to other folks? So in this case, we want to find a percentile. So one way to describe her location in the distribution is to calculate the percentile. The percentile is an individual's percentile is the percent of values in a distribution that are less than the individual's data value. So we're looking for those that are less than. So if you look at Jenny's percentile, this places her fourth place from the top of the class. So how do we go about calculating this? All right, so let's go ahead and calculate her percentile. So if you look at her placement right here, notice that there are 21 observations here that are lower than hers. So 21 are lower. So this means we can calculate the percentile. So that means that 21 out of a total of 24 observations are lower than Jenny's score. And then we times this by 100, and that will give us 84%. All right, this means that Jenny is at the 84th percentile. So she is at the 84th percentile of her class. All right, so let's look at an example. So we're referring to the same dot plot earlier, so I went ahead and pasted it on here. Find the percentile for Norman, who scored a 72. Maria's test score is at the 48th percentile of the distribution. Interpret this value in context. What score did Maria earn? All right, so let's start with Norman. So if you look at Norman, he scored a 72. And if you look at, so this is his score right here. This is Norman's score. So there's only one guy that scored below him. Therefore, he's at 1 out of 25 times 100. In this case, that's 4%. So Norman scored at the 4th percentile. For Maria's test score, in order to calculate this, well, we know that she's at the 48th percentile. So that means we got to convert that to a decimal. So 0.48. So this is the 48th percentile here. And then there are 25 test scores. In this case, this will be 12. So what does that mean? Well, this means that Maria's score was higher than 12 of the 25 students in the class. Now, since Maria's score here was higher than 12 of the 25 students, this means we could start actually counting them. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So she was higher than those 12. So this has to be Maria's score. This means that she scored an 80. So her score was an 80%. All right, so now a couple of notes that we want about percentiles. The median, also known as the second quartile, represents the 50th percentile. The first quartile, or Q1, represents the 25th percentile, and the third quartile represents the 75th percentile. So this in general, these are called quantiles. So quantiles are where you break up a data point into a certain amount of pieces, right? So in general, a quantile can be called a quartile, which, as we know, quartiles break things up into 25%, right? Can be called a percentile. Percentile breaks things up into 100%, into percents of 1, so 1%. So there are 100 percentiles. There are 4 quartiles. There is also other types of quantiles, such as decile. Decile breaks things up into tens. But the ones that we focused on, notice that were quartiles in the last lesson, and now we are just focusing on percentiles in this lesson. But in any case, just know that the median, or the second quartile, represents the 50th percentile, first quartile 25th, third quartile 75th. A high percentile is not always, notice that it's not always a good thing. So like in the case of test scores, or SAT scores, or ACT scores, a high percentile is a good thing. So if you score at the 95th percentile, that means 95% of people scored below you. So this means that that's a good thing. But when you're talking about for example, blood pressure, you do not want to score in the 90th percentile, because that means that you have your very high blood pressure for your age. So that means that 90% of people have a blood pressure lower than yours. So that may not be a good thing. You may need medicine for that. So high percentile is not always good. So next we're going to talk about how to make cumulative relative frequency graphs. So we're going to kind of walk you through this with an example for the ages of presidents when they took office, the data given below. But to get values of the relative frequency, recall that we divide the frequency by the total frequency and then multiply by 100 to convert to a percent. So that's how we get a relative frequency. To find the cumulative frequency, we add the counts in the frequency column for that interval and all the previous intervals that came before that. To find the cumulative relative frequency, we take the entries in the cumulative frequency and then we divide that by the total frequency, multiplying it by 100 to convert to a percent. So let's show you what I mean for this example with the presidents. So we're going to go ahead and set up another column here for cumulative frequency or relative frequency. So that we can kind of review that. So there are a total of 44 presidents in this distribution here that we're looking at. So we're looking at the first 44 presidents. So to take the relative frequency for the first one, you're going to take the count of 2 divided by 44 and then times it by 100. For the next one, 7 out of 44 times 100. 13 out of 44 times 100, and so on. And then we're going to convert these, we're going to do them on a calculator and then get a percent out of them. All right, so whatever those are as percents on the calculator, that's what you would get. And notice that when you add these up, they should always add up to 100%. Now, that's how you find the relative frequency. To get the cumulative frequency, what we need to do is we need to first start at our interval, which is our frequency is 2 for the first one. All right, and then when we go to the next interval, we're going to take the previous interval and add it to the current one. So the current one is 7 now, and then add it to the previous one is 9. And then take the current one, which is 13 now, and add it to the previous ones. So that means 13 plus 7 plus 2, which is 22. And we're just adding as we go on. So the next one's going to be 34. And then 41, because we're adding 7, and then next we're going to add 3 to get 44. So there's our cumulative frequency. So cumulative means it's building up, so it's building up to that total as you go down. Now to find the cumulative relative frequency put together, you're going to take the cumulative count and then divide it by, in this case, the total. So the total was 44, so we're going to put 44 and then times it by 100, of course. 9 out of 44 times 100. 22 out of 44 times 100, and so on. So for this first one, you're going to get 4.5%. Same for this one, 4.5%. This next one you're going to get for cumulative relative frequency 20.5%, and so on. So I'm going to show you the updated values in the next slide, but I wanted to show you how to actually calculate those, go about calculating them. All right, so real quick before I show you that updated graph or that updated table, let's talk about how to make a cumulative relative frequency graph. So a cumulative relative frequency graph plots a point corresponding to the cumulative relative frequency in each interval at the smallest value of the next interval, starting with a point at a height of 0% at the smallest value of the first interval. Consecutive points are then connected with a line segment to form the graph. So first things first, you got to know that this graph uses a cumulative relative frequency. So you got to be able to calculate that. And then you're plotting points from the cumulative relative frequency on the y-axis. On the x-axis, you're simply going to have your ages in this case. So you start at 0% when you plot your first dot, and then you work your way to the other cumulative relative frequencies. And then you're connecting them with a line segment. All right, so I'm going to show you the updated table. So here's the updated table with the percentages and everything. So notice that the cumulative relative frequencies add up to 100%, and if you were to add up the relative frequencies, you're also going to get 100%. All right, so the leftmost, in order to plot this, the leftmost point is plotted at a height of 0% when the age is equal to 40. Because this tells us that none of the first 44 presidents took office before age 40. So when you have age of 40, you're going to plot 0. When your age is 45, then you have moved on to the next interval, which is this interval now, and then you add up the counts before that. So that means that you're going to be plotting two presidents, which is 4.5% for the cumulative relative frequency, because there are two presidents that were inaugurated before they were 45 years old. And you continue to repeat this. So for the next one you're going to, for 50, then you're going to plot the ones before that, which in this case, if you add these up, it'll be 20.5%, and so on. Okay, so we're going to be using this table to actually plot the graph. All right, so on the y-axis, it's always going to be your cumulative relative frequency. And this one is expressed as a percent since we multiplied by 100. And on the x-axis, we have our age at inauguration. All right, so starting at 0 here, we're going to build our way all the way up to 100, since the cumulative frequency adds up to 100 in total. So we got 0, 20, 40, 60, 80, and 100. For our x-axis, well, this is where we use our data values over here. So we're going to be using 40, 45, 50, and so on. All right, so for 40, as we said, there were no presidents that were inaugurated before the age of 40, right? So this means that the cumulative frequency here is 0. Okay, so we're plotting that at the 0 mark. Now for the 45, if you go to the second interval, the cumulative frequency, the ones that were before that is 4.5%. So 4.5% is around here. For the next one, so for now that we're 50, we do the one before that, so it's 20.5%. So 20.5%, so around here. For 55, our next cumulative frequency is 50%, so it jumps up to 50%. Our next one, 60, is 77.3%. For 65, 93.2%. And then 100%. All right, and then we simply connect them by line segments. Oops, this should be more of a straight line. All right, and there's our cumulative relative frequency graph. All right, and now this kind of graph right here that we just drew, this kind of graph is called an ogive. So that's how you pronounce that, ogive. So an ogive is a cumulative frequency graph. But in this case, we're talking about cumulative relative frequency graph, but if you were to graph cumulative frequency, so cumulative, more specifically cumulative, then we call that an ogive. But if we're doing cumulative relative frequency, it may be called an ogive, but it may just be a cumulative relative frequency graph. So cumulative frequency, regular cumulative frequency is ogive, and then if you're doing a cumulative relative frequency graph, I believe we just call it cumulative relative frequency graph, but you may call it an ogive. But in any case, an ogive or a cumulative relative frequency always has this generic shape where you start low and then you're building your way up to 100%. To the very last one. All right, so now that we got the graph, we're going ahead and pasting that, just copying that graph over to the next problem. So using the same graph that we just drew, was Barack Obama, who was first inaugurated at age 47, unusually young? So we want to be able to interpret, his percentile to see whether he was unusually young. So for part A, all right. So what we do is we want to figure out his percentile, right? So we want to estimate his percentile. So we're going to go to 47 years of age. So that's, around here. Like around here. And then we want to estimate what his percentile is. So we go to the graph. Looks like around here. And then we work our way to the cumulative relative frequency, the y-axis. And it's about 10 or 11%. So it's a little bit above the 10, so I'll say 11%. So we're kind of estimating. So this looks like around 11%. So this means that his inauguration age places him at about the 11th percentile. So his age places him at the 11th percentile. So this means that about 11%, so we want to be able to interpret this, right? So this means about 11% of US presidents first took office at a younger age than he did. So he was fairly young in this case. If he's at the 11th percentile, he's at the lower range for the ages, right? So he is fairly young, or he was fairly young. Relatively. All right, so now let's look at the second part. So if we want to estimate and interpret the 65th percentile of the distribution. Okay, so we're going to go to the 65th percentile. So this right here is the 70th percentile. So 65th would be like around here. So we're going to go, so that's about 65. We're going to work our way to the graph. So it looks like around here. And then we want to go down down to the x-axis because we want to figure out what age that is. So like around here. So that's about 58 years of age. 57, 58 is a little bit above the 57 mark, I would say. So about 58 years of age. So what does that mean? Well, it's saying that the 65th percentile, first off, 65th percentile is about 58. So this means that about 65% of all US presidents were younger than 58. So you were younger than 58 when they took office. So drawing this cumulative relative frequency graph actually helps you out tremendously when we're talking about percentiles. You can get information about relative positioning, relative location from any data point, really. All right, so the next thing we're going to be discussing is the standardized score, or the z-score. So a percentile, we mentioned, is one way to measure location, one way to describe the location of an individual relative to other points in a distribution. Another way to do this is the z-score. So the standardized score for an individual value in a distribution tells us how many standard deviations from the mean the value falls, and in what direction. So to find the standardized score, you need to compute the following using the following formula. So again, the value, we'll call this x, or xi. The mean, we'll call that x bar, or mu if you're talking about a population. So x bar or mu. But usually we use mu. And then the standard deviation, you can call it s, or lowercase sigma if you're talking about population. So assuming that we're talking about a population, then, which most of the time you're going to be doing this for everybody, so you're going to be generally doing it for a population, so you're going to be using the following formula. Z is equal to x minus mu divided by lowercase sigma. So this is your formula using the symbols. All right, so then what does this mean? Well, if you get a positive z-score, then that means that the value you have is bigger than the mean. So for example, if the value is 20 and the mean is only 10, well, of course you're going to get a positive number. So that means that you're going to get a positive z-score. And if the value is smaller than the mean, so for example, 5 minus 10, the mean being 10, then of course you're going to get a negative number here, which means you're going to get a negative z-score. So this actually tells you, it gives you direction, like what direction does the value fall. All right, so looking at the same data scores from before, from Mr. Pryor's first statistics test, I went ahead and summarized the statistics for you. So we got the mean, so we got the population mean for every single person in that exam and that class, and then we got the standard deviation, so the lowercase sigma there, and then we got minimum. We got basically the 5-number summary as well, right? So this right here is the 5-number summary. But we also got other statistics in there, such as sample size, and so on. So where does Jenny's 86 fall within the distribution? So let's calculate this for Jenny. So in this case, to find the z-score, well, we got z equals x, that should be x, not x bar, x minus mu divided by sigma. So her score is an 86, so that's her x, that's the x. Now we know what the mean is. The mean is 80, so 86 minus 80 divided by the standard deviation is 6.07. All right. So in this case, we get a standard deviation of about 0.99, and it's positive. So what does that mean? Well, this means that Jenny's test score is 0.99 standard deviations above the mean. Score for the class. So she's about 1 standard deviation above the mean score. So usually, if you're 1 standard deviation above and 1 standard deviation below, you're generally what we consider typical values. Okay, so that means the typical values are, 80%-ish, and then one standard deviation above that, one standard deviation below that. So 80%-ish and about Jenny's score of 86, and probably about a score of 74 would be typical values for the class. So if you look at the average, right, this is the average, and Jenny's score is about 86, so she's one standard deviation above it. So we say she's 1 sigma above it, and probably a 74, around the 74 would be 1 standard deviation below, right? These are considered typical values. So these are considered, typical test score values for this test. Now, if you're more than 1 standard deviation away, then you start getting to atypical values, right? Where these values are not very common at all, right? They're more rare. Same place in the other direction. If you're going -2 sigma, right? Or if you're going +2 sigma or above, then those are considered atypical values. All right, so find the standardized score for Lionel, who earned a 67 on Mr. Pryor's first statistics test. Interpret this value in context. So we're going to be doing the same thing here. So for Lionel here, his z-score is going to be, well, we said that Lionel's test score was a 67. So 67 minus 80 divided by standard deviation is -2.14. So he scored lower than the average. That's what that says, that negative. And he scored pretty low on this exam compared to other students. He's negative, so he's basically over 2 standard deviations below the class mean. So relative to his peers, he's not doing very well. In fact, he's doing the worst in the class, right? So, because he's got a 67, and that is the lowest score if you look at here. So Lionel's score is 2.14 standard deviations below the class mean of 80. All right, so z-scores are very useful in order to compare things of different units. So for example, if you had if you had someone, let's say Jordan, who is 7 years old, and he's 51 inches tall, and let's say her z-score is 1, right? And then you have, for example, Zane. He's 9 years old, and he's 54 inches tall. And let's say his z-score is 0.5. Well, then what does that tell you? Well, you can compare these directly. So because even though they're different age groups, right, you can compare the results directly. So for Jordan, Jordan is taller relative to girls her age, right? So because she is 1 standard deviation above the average. So Jordan is taller relative to her age group. And Zane is not as tall relative to boys his age, right? So Zane is not as tall relative to boys his age. So even though he's physically taller relative to boys his age, he's not. So you can use the z-scores to actually compare different results directly and put it in a common scale. So this is where this is really useful, and we'll be using this a lot in future lessons, quite a bit actually. So from here on out, z-scores are going to be mostly the way to go, especially when we do hypothesis testing. Alright guys, so for the next lesson, it's actually going to be chapter 2. This concludes chapter 1. So the first section of chapter 2, we're going to be talking about relationships between two categorical variables. Rather than just one variable, which we've done in this chapter, we're going to focus on two variables.